In the previous tutorial, we investigated the heat equation on a semi-infinite domain given the conditions at position x equals 0 and time t equals 0, and we found that the solution can be written down concisely in terms of the error function of some dimensionless quantity like x over root at. We used the example of the initial condition u of x0 equal to 0 whenever x is greater than 0, and some value t0 at x equals 0, aiming to solve for the temperature field u on the semi-infinite domain x greater than 0. In this tutorial, we will make a connection between this and the concepts of convolution operators and impulse responses to linear time invariant systems that we developed a while ago. It's not as scary as it sounds, so let's see how it works. Suppose we have a metal rod that is now infinitely long in both directions, so that it extends across the entire x-axis for positive and negative values of x. If we have an initial condition u of x0 equals a step function, which means that the temperature is 0 when x is negative and then suddenly jumps up to 1 when x is positive, then we can use dimensional analysis to transform the heat equation into a normalized temperature, which in this case is just u without its units, and a normalized length scale, which is the dimensionless group x over square root of at, and then express our solution in terms of the error function to generate these solutions. If this analysis looks unfamiliar, please review the previous tutorial in this series, as an understanding of how to obtain these solutions is crucial. Our solution can be referred to as the step response of our system, which is terminology from when we looked at ordinary differential equations that can accept some input and get an output, a large class of which we referred to as linear time invariant systems, or LTI systems. Back then, we had a step function in time t as our input, but here we have a step function in space x as our input initial condition. The same ideas can be used here. For instance, if our initial condition was a Dirac delta function, then we would refer to our solution as the impulse response of the system. Recall that to obtain the impulse response, we just need to differentiate the step response, because the derivative of a step function is the Dirac delta function. In our case, we can take the partial derivative of our step response solution from earlier with respect to x, since our step function is in x, and using the fundamental theorem of calculus to differentiate the error function, we will get 1 over 2 root pi at times e to the negative x squared over 4 at, which we will denote g of xt for the impulse response. In the context of our heat transfer problem, the impulse response is a little tricky to interpret because it represents what would happen if there was a single point at x equals 0 that was initially infinitely hot, which is not a physical possibility. That being said, in the context of material diffusion, it can represent an approximation to the response when the initial concentration distribution is fully concentrated, with a fixed amount of atoms packed into a tiny area waiting to diffuse out through our solvent. Either way, the impulse response ends up producing a steadily growing bell curve, which is incidentally the same curve as the normal distribution from statistics, where our length scale is proportional to the standard deviation of the distribution. We can also observe that if we integrate our impulse response over all x at any given time t, the result will always be 1, and this can be understood as a statement of conservation of mass or energy, as the solute mass or thermal energy provided by our Dirac delta function just gets spread out across the region over time. Now, what if instead of a Dirac delta function as our initial condition, we had some general function u of x0 equals f of x? We have solved this type of problem before in the series on ODEs, and the solution is to use the convolution integral, and this time we will use a spatial convolution, which we also briefly mentioned back then. In short, the solution u of xt to any general input f of x at t equals 0 will be given by the convolution of f with our impulse response g, written like this, making sure that our dummy variable tau is a shift in position x, not time t. This corresponds to taking the responses of our system to an impulse at every possible different position tau and adding them all up, scaled by our input function f of tau, which is exactly what the convolution integral does. In the context of PDEs, our impulse response function g of xt can now be referred to as the Green's function of our 1D diffusion equation. Conventionally, Green's functions are written as a 4-argument function capital G of x, x prime, t, t prime, which just allows us to input any arbitrary shift x prime and t prime into our impulse response g of xt. Another convention is that instead of saying we have an initial condition u of x0 equals f of x, we can absorb this into our PDE to make it a non-homogeneous PDE by multiplying f of x by a Dirac delta function in time to account for the fact that this term only takes effect at t equals 0. We then get the forced diffusion equation partial u partial t minus a partial squared u partial x squared equals f of x times Dirac delta of t, where f of x is our starting distribution. This should now look even more like the examples we saw with ODEs, where the forcing function f of x is on the right side of some linear differential operator, because the initial conditions for this PDE are technically now 0 at time t equals 0. Our general solution, or forced response, to a given input f of x is then given by the convolution of f with our Green's function, which is given by this integral over x, using the new notation. This is also fundamentally why integral transforms, like Laplace transforms and the Fourier transforms, work to solve PDEs. They exploit the convolution theorem that these transforms obey. Green's functions can be found for a wide range of PDEs, not just the diffusion equation, including Laplace's equation, the wave equation, and many more, and by integrating their product with any given initial conditions, we can immediately write down an integral solution. That concludes our analysis of the diffusion equation. The study of partial differential equations in general goes far, all the way to the current frontiers of math research, and believe it or not, we've barely scratched the surface in this series. For the time being, this is as far as we will go. Having studied some general techniques applied to the 3 main classes of linear second-order PDEs, which are the most common types of PDEs that you are likely to encounter up to graduate-level science or engineering classes, you now have the tools to tackle a very wide range of problems pertaining to modeling the natural world. But now, for the last time on partial differential equations, it's time to check comprehension.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.